Welcome to a lesson with Dr. Powell. Let's talk about what it means for an improper integral to converge or diverge. So an improper integral is one with a problem point at an endpoint or in the middle somewhere. So, for instance, if we have something like x to the negative 1/2, and we're going from 1 to infinity, what does that look like? So x to the negative 1/2, that's like 1 over square root of x. So as x gets very large, this whole thing is going to 0. So it's going to come down and get close to 0 down here. So the question is, if we find the area from 1 onward like this, is the total amount of area here under the curve, is that area finite or infinite? It does happen sometimes that the area under a curve actually, even though we're going out forever, happens to be finite. That has to do with a situation like this. If we're walking across a room, first you cross halfway, then you can cross half of that, then half of that, then half of that, and half of that, and so if you add up all these, then half ofs, half ofs, half ofs, half ofs, eventually you end up getting uh, one whole room length, right? One whole room length. So you could picture that as rectangles, if you will, in distances. First you do a half, then you do a fourth, then an eighth, and so forth. So if you add up these, if these each have width 1, we're adding up, we do this forever, we should get a total area of 1. And even if like I drew a curve like this, which is even less than that goes to this point. So let's think about what this curve is. We could say even at this point, so it's going to be a half, we could even say something like this is 1/2 to the 1, this is 1/2 to the 2, 1/2 to the 3. We could even label our function as 1/2 to the x. And so finding the area under the function 1/2 to the x as we go right here is even less than 1. It's finite. So it does happen sometimes. That has to do with if this is decreasing fast enough, we can actually get a finite area. So if it has a finite area, we say that the integral would converge to a value. But if it doesn't, if it seems to go off unboundedly forever, then we would say that it diverges. So the question is, does this integral converge or diverge? If it converges, can we find a value? If it diverges, then we don't find a value. We just say it diverges. So let's work through that and see what we can come up with. All right, so let's backtrack right over to where we were. So we have this, and let's discover what we got. All right. So we have one problem point. The one problem point is the infinite one. We can take an antiderivative. So we end up getting x to the 1/2 divided by 1/2, which is like multiplication by 2. And then we're going from 1 and then up to a value. And let's just say if the value is n, where that n is going toward infinity. In fact, we could even rewrite this as follows. We could say it's simply the limit as n approaches infinity in this situation. So this would be equal to 2 times n to the 1/2 minus 2 times 1 to the 1/2. Okay, but the limit as n approaches infinity. Now, it should be pretty clear that this right here heads off to infinity. So this whole thing is infinite, goes to infinity. It's the limit, which means this integral actually diverges. This integral, so this function right here, does not go down to 0 fast enough. So we get that it diverges. Now let's look at another example. what if we have something like, let's do x to the negative 1/2 again, and let's go from, this time let's go from 0 to 1. So where's the problem point? It's at 0, because you can't plug 0 into this, because that's a negative power. Remember, this is 1 over the square root of x. You can't plug 0 in. So there's a problem. So when we write this out, we take an antiderivative, as we had before. We're going to have 1, but then here, maybe we can use an n value or a value, whatever. I'll just use a this time. So a is approaching 0, but now from the right side, because we're in the interval from 0 to 1, and we're heading to 0 this way on within the integral from the right. So this is what this will be, and we can rewrite this if we want as the limit as a approaches 0 from the right side, and erase this. Okay, so we can think of it that way. And this would be 2 minus 2, a to the 1/2, and we're taking a limit as a approaches 0 from the right side. Now notice this limit actually exists. We can put 0 in and we end up getting nicely, and so we end up getting 2. So it looks like this integral is 2. Let's look at the graph of x to the negative 1/2 again. That graph looks something like this. Now, as we approach this, it looks like this isn't going down to 0 fast enough. So we know that on this side, as we integrate over here, that diverges. However, flip side, if we go from 0 to 1, we're going this way up here, and we actually go to 0 fast enough over here, so it actually converges. Whenever we have a power function like this, we'll actually notice that. On one side it converges, on the other side it diverges. Flip-flops it. The only time this doesn't happen is with the power of x to the 1. Or x to the negative 1, I mean. X to the negative 1. Okay, x to the negative 1 is very symmetric. So it's going to be the same over here as over here. And it actually diverges in both cases. But aside from x to the negative 1, x to the negative, if we have x to the negative anything else here, we'll always have one side converging or one side diverging. In fact, why don't we look at one more quick example here of that? What if we had something like 1 to infinity of x to the negative 2? Okay, so antiderivative would be x to the negative 1 divided by negative 1. So it would be that as we go from 1, and n is heading toward infinity. Now, this is the same as negative 1 over x. And as n goes to infinity, that's limit of that is just going to be plugged in for x is going to be 0. And then right here, when you plug in a 1, you can get minus 1 over 1. So you have minus, well, it's going to be minus a negative 1 over 1, which would just end up being a positive 1. So this integral right here ends up being just simply positive 1, so it definitely converges. Notice that this power function, okay, as we're looking at right here, is x to the negative 2 when we graph it. It actually, over on this side, it'll actually converge. Before, for the other one, it diverged, but this side it converges, and you'll actually notice if you work it out, then on the other side, it would actually diverge. In fact, you can kind of see that because on the other side, you're going to be throwing a 0 into this antiderivative, and notice what that would blow up in the antiderivative. That would cause a divergence on that side. Here, though, if we're going toward infinity on this side, that's kind of nice. I mean, that causes a 0. So when we plug it in, or when we take a limit rather, and it would be converge on that side. So just a few notes about what it means for integrals to converge and diverge. And in particular, we investigated this idea for power functions a little bit. Thanks for watching.